Hello everybody, my name is Stadtmüller. I'm from the University of Kaiserslautern in Germany, and today I'm going to give you a flavor about my presentation that I'm going to give at the Focus PEEM workshop in 2021. In this presentation, I will particularly focus and demonstrate the capabilities of photoemission electron microscopy to study molecular materials in real and momentum space. So molecular materials have fascinating properties that allow us to create novel devices such as this flexible solar cell or this very colorful light-emitting diode technology that we all know from first demonstrator devices. And there are many advantages that make these organic materials so appealing for next generation of electronic or even spintronic devices, such as the fact that they can be grown on flexible substrate and that they have low spin-orbit coupling, which is particularly important for spintronic application. However, for all this application, the most important advantage of molecular materials is their chemical tunability, which allows us by chemical synthesis to chemically change the size of the molecular complexes, change the shape, going from benzene-like planar molecules to a 3D object like these buckyballs or C60 fullerenes. And by changing the geometric structure, we have a very easy handle to alter the electronic properties which are imprinted in the energetic position of the valence orbitals, naming the highest occupied molecular orbital, the HOMO, or the lowest unoccupied molecular orbital, the LUMO. The most important thing between the connection of chemical tunability and its electronic properties is the band gap of the material, which is ultimately responsible for the color of the organic materials when they emit light, or for the absorption spectrum of molecular materials when they absorb light. So we have a unique possibility to chemically functionalize this device-relevant properties of the material. However, like always in life, there's a catch, and the catch is that as soon as we bring molecular materials in contact with metal contacts, in contact with each other, then we have severe changes of the electronic properties of these materials. For instance, we can have broadening of the electronic levels, we can have band shifts and band structure renormalization of the molecular valence and conduction level, which leads to a change in the band gap, or we can, in certain cases, as it is shown here, can also experience charge transfer from the substrate into a molecular material that then changes the occupation of the molecular orbitals. And these changes can be correlated to the interaction in the system. For instance, for molecules on metal surfaces, the hybridization, or at least interaction between substrate or metallic states and molecular orbitals results in this charge transfer or shift of the states around the Fermi level. For higher coverages in the multilayer, molecule-molecule interaction can also contribute to the changes of the energy level alignment. So therefore, in order to enhance the capability and performance of such devices, it is necessary to understand the energy level alignment of molecular materials on surfaces or molecular materials in molecular thin films. Of similar importance is the light to charge conversion process that dominates photovoltaic applications, or the charge to light conversion process that dominates, for instance, organic light emitting diode technology. And therefore it is important to understand the light-matter interaction in molecular thin film on surfaces, to characterize the light absorption, and to study the dynamics of the created charge carriers, which is dominated by excitonic effects and charge transfer phenomena, for instance, from the molecular material into the substrate, which is typically a metal. And in this presentation, I will give you a flavor and I will show you our approach, how we can use photoemission electron microscopy to learn more about this fascinating physical phenomena that occur in molecular thin films or molecular metal hybrid systems. For these fundamental studies, we don't consider large stacks of multi-layers of different materials like metal, organic, metal tri-layer systems, but we focus on model systems which are typically a highly crystalline molecular thin film starting with one layer up to a few layers that are grown in a controlled fashion on metallic or semiconducting surfaces. And we use now photoemission electron microscopy with static light sources to image either the real space and K-space signatures of these molecular thin films. And from real space, we can create real space images of the sample surface with a larger magnification where the contrast is given by, for instance, the work function of the molecules. And from this we can learn something about the growth kinetics of the molecules, the morphology, or the island size of the molecular materials that we have grown on the surface. Switching to momentum space mode of these devices, we can address the electronic properties and look at the molecular band structure or at molecular metal hybrid interface states that can arise at interfaces between molecules and metal surfaces. And I will show you how we can use this kind of information in order to correlate the electronic properties to the interactions in the system. I will also show you a different approach by using the same imaging techniques, but combining them not with continuous wave light sources like helium discharge lamps or synchrotron radiation, but with femtosecond light pulses. I will show you how we can use pump probe spectroscopy with femtosecond pulses and femtosecond time resolution to learn something about charge transfer phenomena in molecular thin film or about exciton dynamics in molecular crystals. And with this introduction, let me close by giving you a few ideas what I will talk about in detail. So in the first part of my presentation, I plan to talk about static properties of the band structure of fullerene complexes on surfaces. I will show you that molecular thin film can also exhibit an atomic-like band structure, and therefore I will use molecular complexes such as this fullerene complex C60. I will also go a step further and discuss the electronic properties of interhedral fullerene complexes where we have a carbon cage, in this case C80, which encloses a small group of atoms, which in this case are 3 scandium atoms that are coordinated to a nitrogen atom. And I will show you how we can use momentum microscopy or photoemission electron microscopy operated in momentum space in order to demonstrate that on surfaces this inner cluster of atoms can be severely influenced by charge transfer. In the second part of my presentation, I will move on to the ultrafast time domain, and I'll show you how we can use, again, photoemission electron microscopy in momentum space mode to study the exciton formation and decay process of excitons in molecular thin film. And in particular, I show you our first step towards understanding conversion processes from charge transfer to Frenkel-like excitons in this material. And with this, I hope I've raised your interest, and I would be very happy to welcome you at next year's workshop and discuss with you about exciting science that we can study with photoemission electron microscopy in molecular thin films. Thank you very much and see you next year.